So welcome back, students. In the previous video, we talked about the electrostatic properties of a conductor. We talked about 4 such properties. And now I just want to expand on it. I just want to focus on one case which will elucidate the concept very well. That is this. See, when we discussed the first lesson, electrostatic force and fields, we came across a problem where you had 2 spheres of equal size, either 2 identical spheres, and one was charged to a certain extent Q, and then like you touched it with another sphere, and there was this charge sharing that took place between the 2 spheres. So we said if the 2 spheres are identical, then you'll have the charge on the on one sphere, and the remaining half would be on the other sphere. So this is what we discussed in the first lesson. We did not talk about what would happen if the spheres were of different size. So that is what we are going to talk about now. Let's do this. Let me take 2 spheres, metallic spheres. This is sphere 1, and it has a radius R1. Okay. And or I just have a small r, the small sphere, so I'll have small r. Okay. And it also has a charge Q on it right now. I mean, the charge could be 0, the charge could be anything. I'm taking a very general case. So you have a small sphere with small q charge on it, and that sphere has a radius r. Now there is another sphere, a big sphere, or a bigger sphere than this, that has capital Q charge. Let's say a sphere like this. Okay. So this has capital Q charge, and then the radius is capital R. Now I am bringing these 2 spheres in contact. So as we know, there must be a charge sharing. So how will the charge be shared in this case? The charge will not be shared equally. The reason is that they are not identical spheres. One sphere is smaller than the other sphere. So let us see how to do this problem. Okay. So you have one sphere that has small charge Q, and you have another sphere which has big charge Q. So you are bringing them in contact. Well, so because of the respective fields, then the charges on these spheres will start moving, but then they will quickly reach an equilibrium condition. Electrostatic condition will be reached, where the charges will not move, but then they will rearrange themselves in a certain way. Okay? So how would that be is a question. Well, to start with, we need to remember that when you bring these 2 metals in contact, then they become a single metal, right? A single conductor now. These, the conductor 1, conductor 2, then you bring them together in contact and they become a single conductor. And what we know about from the properties of the conductor, the electrostatic properties of the conductor, which we discussed in the previous video, that on a conductor, the charge will be distributed along the surface of the conductor, and then the field inside the conductors will be 0, and the potential will be the same at every point on the conductor and also inside the conductor. So we said E will be 0 and E will also be 0 here, and then the potential V will be the same for both of them. So that is when the charge movement will stop. I want you to understand this. Let me repeat. You have two conductors, conductor 1 and conductor 2. They have two different charges. You are bringing them together. Okay? Now, when you touch them, they become a single conductor. So the charge will get distributed around the conductor. And when will this charge distribution stop? When the charges have distributed themselves around the conductor in such a way that this condition is met. E inside the conductor must be equal to 0 and V will be the same throughout the conductor. So V will be the same here and V will be the same here. So you have V here and then you also have V here. V must be the same. Okay? So this V1 and V2 must be the same. Okay? So that is when the charge distribution will stop. Till then, charges will start moving, aligning themselves. And once the potential is the same everywhere, then it will stop. So that is the final state. So in the electrostatic state, V will be the same across both the conductors because they are in contact with each other, so they become a single conductor. And E will be 0 inside. Keep that in mind. So now let's see. So the potential on this conductor must be the same as the potential on this conductor. So what would be the potential on this conductor? So let us suppose that Q1 is a charge distribution there. Okay. So Q1 is a charge distribution. And then Q2 is a charge distribution here. Let's see what happens now. Q1 plus Q2 must be equal to Q plus Q. Okay? So, this is the total charge you start with. Q plus Q is the total charge you start with. And when you bring these two things in contact, this will have Q1 and this will have Q2. And what else do you know? You know that V1 is equal to V2. In the electrostatic condition, V1 will be equal to V2. But what is V1? Because I can treat this to be a spherical conductor, and Q1 is a charge on that conductor. So the potential of this conductor will be, so V1 should be equal to K Q1 by small r. That will be the potential. Because Q1 is a charge on this conductor, so just touching it there. So the potential can be calculated like this, K Q1 by r. And what is V2? So V2 is also equal to K. Now Q2 is a charge on this conductor. Okay. So Q2 by R. And what do we know? We know that V1 is equal to V2. So K Q1 by R must be equal to K Q2 by R. So how do you do this then? I can say like this, Q plus Q, that gives me some number, okay? Let's say that is N or something, okay? So this N is actually Q plus Q. If I add these two, then that's a total charge, okay? So that's the, maybe I'll call it as QT, right? That's the total charge, QT. the charge that you started with, Q plus Q. Okay. So then what is Q1? I can say Q1 is equal to Qt minus Q2. From this equation, I can call this as equation 1, I can call this as equation 2. So from 1 I can write Q1 is equal to Qt minus Q2. Like then, can I substitute that in this equation? So what would I get here? K into Qt minus Q2 by R is equal to K Q2 by R. So I bring it here, R, so that gives me K QTR minus K Q2R equal to K Q2 to small r. I've taken R to the other side and I've taken this R to this side. So then I can rearrange, right? I can get Q2 on one side now. So Q2, if it goes there, K Q2R plus K Q2R, small r is equal to K QTR. I can cancel K. Then Q2 is equal to Q2 into R plus R is equal to Qt to R. So Q2 is equal to Qt R by R plus R. Okay? And you see this Q2 is actually Qt to R by R plus R. So if I do the same thing with Q1, then I will get Q1 is equal to Qt to small r by R plus R. So you can see this. So the smallest, look at these two. So this is Q2, this is Q1. Q2 is the same, R plus R is the same, and R plus R is also the same. So notice that the charge that this will get is proportional to the radius, and the charge it gets is proportional to the radius. So you can say that the charge that you get is actually Q is proportional to the radius. So the smaller the sphere, the smaller the charge on it will be. Then the bigger the sphere, and the bigger the charge on it will be. So this is how the charge will be distributed. So let's come back to the original problem. The problem that we faced in the first lesson. What if both the R's are the same? You see, this is R, this is R plus R, 2R, so R by 2R, so 1 by 2, so Q by 2, then Qt by 2, so the initial charge by 2, initial charge by 2. So if the spheres are identical, then the charges will distribute equally. But the spheres are not identical. If they have different sizes, then what happens is this. Depending on the radius, then the charge which is shared by the spheres will be different. So this is the first part of it. And there's also a second part where we are going to see what happened to the charge density. We have seen the charges. what will happen to the charge density? Why should we be worried about the charge density? Remember, the electric field intensity depends on the charge density. That is the derivation that we had in the previous videos. Like when you have a conductor and near the surface, what would be the value of the electric field? That was equal to, E was equal to sigma by epsilon naught, if you remember. So the charge density is important in that respect. So I can find what the E value will be here and here. So to know that, I should know the charge density. Now I know the charge. I know Q1 will have this charge and Q2 will have this charge. But what would be the charge density, and thereby what would be the electric field intensity near the two spheres? That is something that we will discuss now. So this was the inference we had. Qt was the sum of the initial charges, small q and capital Q. Then we brought these spheres together in contact. Then the smaller sphere had Q1 on it, and then the bigger sphere had Q2 charge on it. Then Q1 is given by this expression Qt into small r divided by r plus r, and then Q2 is equal to Qt into the capital R divided by capital R plus small r. So this is what we have just derived. But now I'm going to find out the surface charge densities of these two spheres. So sigma 1, what is the surface charge density of this sphere? Sigma 1 is equal to Q1 by the surface area of this sphere, which is A1. So what would I get here? So what is Q1? Q1 is Qt to R, small r divided by R plus R. Now what should I be doing? Then I need to divide the whole thing by the area. So what is a surface area of a sphere? 4 pi r squared. So I'm going to do it here. So 4 pi r squared. So that gives me, after cancelled this r with the r squared, it's going to be Qt by r plus r into 4 pi r. That is sigma 1. And what about sigma 2? That is surface charge density of this sphere, the bigger sphere. Sigma 2 is equal to Q2 by A2. So what is Q2? It's Qt into capital R by R plus R. And what is A2? That would be 4 pi into capital R squared. So 4 pi capital R squared. So this R and this square will be cancelled. So this will give me Qt by R plus R to 4 pi capital R. Okay, so notice that sigma 1 is inversely proportional to the radius. Sigma is inversely proportional to the radius. Qt is a constant because the initial charges will not vary, the total charge will not vary. Then this r plus r is also a constant, that won't vary. 4 is a constant, pi is a constant. And now you have this r. Okay. So this sigma 1, if you do sigma 1 by sigma 2, let's do it. Sigma 1 by sigma 2, and note that you have Qt by r plus r into 4 pi r divided by Qt to r plus r to 4 pi r. QT and QT will cancel, 4 and 4 will cancel, 5 and 5 will cancel. Then what I'm going to get now? I'm going to get capital R by small r. So the surface charge density of this one depends on this radius, and the surface charge density of this one depends on this radius. Okay? You see that the situation is reversed. When we talked about the charge sharing, so the smaller the sphere, the smaller the charge on it. The bigger the sphere, the bigger the charge on it. But then when we calculated the surface charge densities, and clearly the smaller sphere will have a bigger surface charge density than the bigger sphere. Okay? So that is kind of counterintuitive. So if this is the case, what do you think would be the nature of the field near on the surface? Okay? We said E on the surface is equal to sigma by epsilon naught and then the normal, right? So if I take this point, for example, what would be the E here? Okay? So that is equal to sigma epsilon naught into this unit vector. That would be the direction of the normal at that point. Okay? We know that. So E1, which is a field here, this point. Okay, E1 is going to be equal to sigma 1 by epsilon naught. Okay, and it will have a direction, some direction here. And then what about E2? E2 is equal to here, that's sigma 2 by epsilon naught. And it will also have a direction. For example, we take this point, then it may have something like that. So notice here, E2 will have a smaller value than E1. Okay? It's an important result. You have to think about it a little. So what have we done here? First, we calculate how the charge is going to be distributed between the two spheres. We found out that the smaller the sphere, the smaller the amount of charge which would be on that sphere. That's wonderful. Okay? That's understandable. Then we calculated the surface charge density of those two spheres. And then we found out that the smaller sphere will have a greater surface charge density than the larger sphere. Okay. And because the smaller sphere has a greater surface charge density, the electric field on the surface of it will be greater than the electric field intensity on the surface of the larger sphere. Okay, so that's kind of counterintuitive. So for example, if I have a conductor like this, big conductor, okay, and then maybe there's a smaller sharp edge here, a sharp edge there. Okay, I can treat the sharp edge as a collection of small spheres, right? So for example, if it's it's can written as small like that, spheres in contact, and then this big sphere. Yeah. So you have a conductor and then you have a sharp edge in that conductor. Notice that this field strength is going to be much larger than the field anywhere else. This field strength can be really strong. So on the sharp edges, the field strength is very high. So see, when you make a conductor, if you're making the surface not as a perfectly smooth surface, which is impossible for you to make, right? It's very difficult to make a perfectly smooth surface. Sometimes you may have a very sharp edge somewhere. So what happens is that at those sharp edges, then you will have very strong field. So you have field here, you may not even realize that you have a sharp edge there. And then you have E here. You may assume that this will have the same E here, because it looks like, so they are uniform. But while manufacturing, if there is a small edge, a sharp edge there, then this point will have a much greater electric field than the other points. Well, the charge on it will be small. Okay, there's no question about it. That's what we found. But the surface charge intensity would be high, and since the surface charge intensity is high, the surface charge density is high, the electric field intensity will be very high too. Okay, that is what happens if you recall when you go and touch a doorknob, a metal doorknob during winter. So I told you during the first lesson that when you walk on the floor, because of triboelectric effect, then you yourself get charged. Okay? Because this friction gives you charges. So your body is right now it's charged. You may not realize it. Okay? During winter, particularly when the air around you is dry, so you may even walking on the floor would charge you. You will have some charge there. So you have some charge. So you have some charge. So what you do, you just go try to touch the door. Okay, like the handle of the door. Okay. So how do you go? You generally go like this, right? When you go like that, you see, if you consider yourself as a conductor, these are sharp edges. Okay. So even though the charge is distributed around you, the extra charge is distributed around you, the charge will be small here because it's sharp edge, but then the surface charge density will be much higher at sharp edges than on the other parts of the body. The charge will be less, but the charge density will be much higher here. So when I go here, so the electric field due to the charge will be very high that it can even ionize the air between you and then the doorknob. Okay? So it can be very strong. The field can be very, very, very strong. Okay? But it can ionize this doorknob. So what happens is that it provides a path for the so what will happen if the air is ionized? Then you have positive and negative charges there, right, in the air. So then they get attracted to your hand. Okay, so when the one type of ions like get attracted to your hand, and the current flows through your hand, and then you feel a shock. So that is exactly what is happening. Okay. So why do you have a shock? You have a shock because of this. What happens here? What happens here is that at sharp edges, the surface charge density can be very, very, very high. Because the surface charge density is high, it will result in very high electric field intensity. When the electric field intensity is high, it can even ionize the air between you and then the doorknob. So current can flow into your body. When current flows into your body, then you feel the shock. All that happens because of this. So to summarize, when you have two conductors, one of them or both of them can have charges. They may be of equal or the same sizes. When you bring them in contact, what happens is that the charge sharing takes place. And then the criterion by which you will calculate the charge sharing is this. When will the charge sharing stop? When the potential across both the conductors will be the same. They become one single conductor. And one single conductor with charges on them, we know that the potential must be the same throughout. Then the charge sharing stops. So V1 on one conductor must be the same as V2 when they touch each other. And if there are spheres, then you can calculate how the charges will be distributed between the two spheres. So we saw it here. The smaller sphere will have smaller charge, and the bigger sphere will have a bigger amount of charge. Okay, but then the charge density will be different. The charge density on the smaller sphere will be greater than the charge density on the bigger sphere. Because the charge density on the smaller sphere is greater, the electric field due to the charge density, electric field on the surface of that sphere will also be different. And if the charge density is greater, then the electric field will be greater. The charge density is smaller, then the electric field will be smaller. So sharp edges will have high electric field intensity, higher electric field intensity than the rest of the conductor. And sometimes the electric field intensity can be very strong, that can even ionize the air around it. When they ionize the air around it, the charges can leak into the air. Okay? Or the ionized air can come and neutralize some of the charges. Okay? So charge will start leaking. We call that as leaking into the air. Or you can say that so charge flows into this conductor and then starts neutralizing the conductor. So you will start losing charges. So this can be avoided only if you have a perfectly smooth surface. If you don't have a perfectly smooth surface, then leaking is inevitable. The conductor will start losing the charges, and sooner or later you will be left with no charge. Okay, roughly no charge. Okay? Again, depends on. I should say not no charge. It starts leaking till you reach a point where E, the electric field intensity, is not strong enough to ionize the air around it. Then it won't leak, the charge won't leak, and that charge only will remain. Any more charge will leak into the air. Okay? But these equations are very important for you. So Q1, say Q is proportional to R, but sigma is proportional to 1 by R, and E is proportional to sigma. Okay? So keep this, and that is what we found out. Hope it's clear to you. The next topic that we are going to talk about is the dielectrics. Okay? Actually, like we'll talk about both dielectrics and polarization. Okay? Say this: dielectrics and polarization. Okay. So first of all, what are dielectrics? Dielectrics are basically insulators. So you have already talked about conductors, and now we'll talk about insulators. Okay, so we call them as dielectrics. Okay, you see, if you take a non-conducting material, then you get two types of materials basically: the polar substances and also non-polar substances. There's a polar and non-polar. So dielectrics are not conductors, conductors and insulators. Right? Conductors have covered already, and then dielectrics. The other way of saying insulators. Okay? So if you take this, you have polar and non-polar. So the polar molecules, an example I can give, or say water, H2O, and say HCl. These are polar molecules. What do you mean by polar molecules? See, and okay, then non-polar molecules. Non-polar molecules, you take oxygen, okay, or carbon dioxide, and these things are non-polar molecules. How do you classify something as polar and non-polar? See, if you take a non-polar molecule, the net positive charge and then the net negative charge of that molecule will be at the same point. For example, let me take an atom. So you have the nucleus where you have positive charges, and then you have electrons going around, right? So it could be many different orbits, and in those orbits, electrons could be going around. So if we take the center of the negative charge, okay, then that would coincide with this, the center of the positive charge. I mean, it's average center, average position. Think about it. Why? Because you see, if it is like this, the electron is going to spend equal amount of time here and also here, right? So if I time average that out, then I can say that on the average the electron was here. Okay? Because sometimes it's positive, sometimes it's negative, equal amount of time positive, equal amount of time negative. So I can say that it is at the very center. The average position is the center of this, right? And anyway, the positive charges are there. Okay, so now you get the net charge, the average charge that you see for a person who is outside would be 0. Because the positive charge center is this, and the negative charge also behaves as if it were here. Why? Because it spends equal amount of time here, and equal amount of time here, and here, and here, and here. And all these places spends about equal amount of time. So both the positive charge and the negative charge centers coincide, resulting in no net charge for the outside world. So you won't find any net electric field or something. So these are called as non-polar molecules. I mean, here I just talked about one atom, but then if you take a molecule also, this will be the case. In the case of non-polar molecule, suppose the positive center is here, and then the negative center will also be at the same place where you will find the center for the positive charges. So pretty much the same thing. Okay? So, but if you take the polar molecules, the centers are going to be slightly different. You won't find the same center for the positive and the negative charges. For example, if it is slightly skewed, I'm just doing it this way. Suppose the positive charge is here. Suppose it follows a path like this. It's not exactly correct, but suppose the electron follows a path like this, not exactly circular. You see, if I were to find the center of this path, it will be somewhere here, right? So this is positive and this is negative. You notice the normal circumstances, the positive and then the negative centers are separated by a distance normally, because the revolution of electrons around the nuclei in those molecules which are polar would be something similar, resulting in slightly different positive and negative charge centers. So if I take a point here, for example, it is closer to the negative charge than the positive charge. So what happens on the average? What happens is that the negative, the force of the effect of the negative center will be greater than the effect of the positive center, resulting in an electric field here. But that won't happen here, because if I take this point here, both the positive center and the negative center, since they reside in the same place, then if the positive charge is pushing this out, the negative charge is pushing this, pulling it in, resulting in cancellation of both, and resulting in no net force, no net field at this point. So this is non-polar and this is polar. For example, if you take HCl, so like the H is a smaller atom and then Cl is a bigger atom. Okay, so this would be more positive here, and then this would be more negative here. Why? Because this is ready to donate an electron, right? Hydrogen is ever ready to donate an electron. So this will become positive, and the electron will circle around the covalent nucleus more. So, so you'll have a dipole moment there. Okay? So if you take oxygen, water if you take, so you have oxygen here, O here, and then you have H, and then H here, so H here. You see, the oxygen will try to pull electrons towards itself. So the electrons will spend more time on the oxygen side than on the hydrogen side, resulting in negative center getting shifted towards oxygen. So negative would be here, positive would be here. So the dipole moment will be something like this. So water and HCl are permanent dipoles. Okay? So these dielectric materials are polar materials. They automatically they are polar. So when the material is polar, then it's going to have a dipole moment. Each molecule will have a dipole moment. But when the material, the substance is non-polar, then they are not going to have a dipole moment, because both the positive charge and the negative charge centers coincide with each other. Okay? But then, what happens when you subject a non-polar material to an electric field? You see, okay, suppose this is a positive center and this is a center, positive and negative charges. Now, I am keeping this molecule in the presence of an electric field. So what is likely to happen? The positive charge will go this way, and the negative charge will try to go this way. So the centers get slightly disturbed. It's like there is a stretching that is happening. Right now they are together. The positive center and the negative charge center are one and the same. Now I am bringing in an electric field. The positive charge will go this way. I said the positive charge will go this way, and the negative charge will go this way. You see that there is a separation. So when there is a separation, then you will have a dipole moment. Now you will have a net field due to this somewhere here, around this. Okay, you won't cancel now. Previously it was cancelling. The field of the molecule was cancelling. But now that you have kept it in an electric field, and then that field has slightly stretched this, now you will have a net field due to this dipole. Okay, so that is what is happening in the case of a non-polar materials. So how will they look like if you think about it? Well, this is one molecule, right? So when you take a substance, it will have lots of molecules, and none of them has any intrinsic dipole moment, because they are non-polar. A non-polar molecules will have no intrinsic dipole moment. So you will have all these things here, right? Plus minus, and then say maybe I say plus minus, plus minus, plus minus. So all these centers are like this. But then the moment you subject them, to an electric field, then what happens is this kind of a situation takes place. So you have this plus minus, plus minus, plus minus. You see, now this kind of they get cancelled, because they are very close, they get cancelled, and then it will result in a net plus on this side. It's very close, right? So it's kind of cancelled, like stretched and cancelled. So you notice now that you have plus charges on this side, minus charge on this side. So it gets polarized. A non-polar material, a non-polar substance with lots of molecules, when it is subjected to an external electric field, then the centers, which were the positive and negative centers, which are together first, are now stretched slightly, and now you get positive here and then negative there. So effectively, then you get a series of positive charges, net positive charges on this side, and a net negative charges on the other side. So it behaves like two parallel conductors where you are given excess charge. Okay. So it's like a conductor. Take this material. Now it is behaving like what? It is behaving like a conductor with positive charges here and the negative charges. And what about the polar materials? The polar materials will have, so polar materials, if you take polar substances, they will naturally, each molecule will have a dipole. Okay, so each molecule will have a dipole, so it's plus, minus, but then they're randomly oriented now. Okay, so it could be like this. So randomly oriented. Okay, so something like this, maybe this is something like that, and say I have minus plus. So randomly oriented. So even though each molecule has a dipole of its own, since the molecules are randomly oriented due to the temperature and the thermal agitation, the net dipole moment of the substance will be 0. But if I subject this polar material to an external electric field, then also this the same thing will happen. Then also this will become, if this is subject to an E, then what happens is this. If it is subject to E field, then notice that you will have minus plus, then you will have minus plus, then you will have minus plus, okay, then you will have minus plus, minus plus, minus plus. So this kind of an orientation can take place here. Okay. So this, the internal things could kind of cancel each other out because they will be very close to each other. And outside, you take this material, and effectively this material also will have a net positive charge on one side and net negative charge on the other side. Okay. I think I've drawn this differently. So positive charges will go this way, negative charges will go this way. But here it is okay. It's negative on this side, positive on this side. I drew the direction and corrected it. Okay. So effectively what happens is, whether it is a non-polar material or a polar material, even though it is an insulator, when you subject it to an electric field, then it looks like, or it behaves as if positive charges gather on the one side and negative charges gather on the other side. But there is a significant, this seems to be happening for the conductors also, right? So when you bring a charge here, then what happens in the case of a conductor? Then electrons will either, if it's a positive charge, electrons will get attracted to that charge, they'll go this side, leaving this net positive and this net negative. So the same thing, something similar was happening in the case of conductors also. So if you look at it, the conductors and insulators kind of behave the same way, but then there is a significant difference. The difference is this. In the case of the conductor, because you have free electrons, they can move very freely. I told you, the example I gave you was a child in your street which can go into any house and then eat from that house. Very outgoing child, extrovert kind of a child. So that was a conductor. The free electrons will move to any atom. So it is possible, I mean, not it is possible. What happens in the case of conductors is that the electrons will move in such a way that during the electrostatic equilibrium, the net field inside can be cancelled. Okay, net field is 0. We'll tell you like why that net field is 0. I'll draw the picture shortly, but I'll come to that. But I want you to qualitatively understand this. We'll do it a little later quantitatively. But I want you to understand it qualitatively. So the electrons can move from this place to a different place. freely. So what happens in the case of a conductor is the net field inside the conductor is 0. We have discussed that. In the case of a dielectric, the charges don't move, the electrons don't move from one atom to another atom, they don't completely move. It is like they are getting stretched like this. Okay, it is like the same example I gave you. A kid which is sitting on the lap or the hip of his or her mother. Okay, so now you are showing it a chocolate, and then what the baby does is it's coming towards you, but then it doesn't really leave the mother. That's the example I gave you for the dielectrics and insulators. So when you subject them to an electric field, they don't leave the atom. In the case of conductor, they leave one atom and get into another atom. So they're free to move around. In the case of conductors. In the case of insulators, the dielectrics, they don't move. They just get kind of stretched. They get stretched now. Like the child on the mother's hips. When you show the child a chocolate, it just tries to stretch and it tries to grab the chocolate. It doesn't leave the mother. A slightly shy child. So that is what is happening in the case of dielectrics. So when this happens, the dielectrics cannot cancel the field out completely. They can only reduce the field. I'll tell you, we'll do the picture now. So in the case of conductor, the field inside the conductor is 0 because electrons can move freely and adjust. In the case of insulators, that cannot happen. There are no free electrons. It is just that the centers are shifted slightly. It's like some kind of a stretching action that is taking place there. And because of that, the electric field inside the dielectric material will not be completely cancelled, but it will be reduced. I will tell you why now, okay, how it happens. So just keep this in mind. In the case of conductor, the field inside the conductor is 0 when you subject it to an external electric field. In the case of a dielectric, the field inside is not 0, but it is reduced. Okay? We'll do it now. I'll draw the pictures for that now, so that you can understand it better. So we said that when you have a dielectric or a conductor, it's like this, and then when you subject it to an external electric field, then charge is gathered here. Let's say it's like this, minus and then 1 plus here. If there is no charge, there is no conductor here, then at this point there would be an electric field. There would certainly be an electric field. If the conductor was not there, then there would be an electric field here. But because you have a conductor there, so what happens is that this field is here at E, but then there is also a field set up by this, right? So that will be in this direction. And then what about this? This will set up a field in this direction, right? So it will be, I'll say this would be EC minus, and also this will be EC plus. E is the external field, and then EC, and then EC plus and EC minus are the field set up by these charges. You see, they are acting opposite to this E. In the case of conductor, they completely cancel. So EC minus plus EC plus, this must be equal to E, resulting in net E. Okay, and then say, I'll say this, okay. So this plus this plus this. When you add all these three, then the field inside will be 0, and that is in the case of conductors. But what happens in the case of insulators or dielectrics? So dielectrics, what happens is, as I said, the field E is set here. If there is no dielectric, at this point there would be a field. But now you keep a dielectric in that space, right? So now what happens is, as I said, there is a stretching activity that is taking place. So resulting in net negative charge here and a net positive charge on the other side. the electrons are not free to move, they just get stretched slightly. They try to spend more time on the one side than on the other side because of this force. They are getting attracted to this. So because of this, what happens if we take this point, now you see you have E, but then what will happen here due to these charges? We have net negative, right? So there also you have electric field with a dielectric in this direction, and there is this charge on this one, right? So that would be electric field due to dielectric, that is positive. That is also in this direction. You notice here, it is acting in the opposite direction. So what is happening here? You have the same AD minus plus ED plus and then plus E will be a net E. Okay. So in this case, these two will not completely cancel out E. Why can I not completely cancel out E? Because the stretching happens because of E. If you, okay, so that's the thing. So as you increase the field, the stretching will also increase and increase and increase, but then they won't exactly cancel out. So here, the net E is not equal to 0. But E net clearly will be smaller than E. Okay? So if the dielectric material was not there, you would have E here. Yeah? But because you kept a dielectric material here, there would be this accumulation of charge on either side because of induction. And these charges will have their own field, and those fields will act in the direction opposite to the direction of the applied field. So the net field at this point will be a reduced value. Here it's completely cancelled. Here they are not completely cancelled, but then the field will be reduced. So this is how the dielectric materials act. Just keep this in mind. E inside the conductor is 0. Let's put it this way. E without any material. If we take a point in space, E at this point will be E, no problem. Okay? And if you bring a conductor here, conductor, then E will be 0 at this point, same point. And if I bring an insulator or a dielectric material there, then I will have some E, okay, dielectric material. I will at the same point, I will have some this point. Even though I have drawn it here, I am actually keeping it here. Okay. I am taking this and then keeping it here. I am talking about this point only. E will not be equal to 0, but E net, I will say. E net will not be equal to 0, but E net will be less than this E. So whatever E you would have had without any material will be greater than the E you would have at that point with some material kept there. Okay? I'm talking about this case, this point. I am setting a field, E value. Now I bring a conductor here. At this point, the E value now is 0. Now I bring an insulator here or a dielectric material here. E at this point is not 0, but it is now less than E without any materials kept there. Hope this is clear to you. So this is how these substances behave. Conductor completely cancels out the electric field, but a dielectric material doesn't completely cancel out the electric material. It reduces the field value by setting a field in the opposite direction. You see. So there is this material, because of this charge separation, sets up its own field, but that field is acting in the direction opposite to the direction of the external field. So the net field at that point is the vector sum of these two, which actually is a reduced value. Okay? I hope this is clear to you. And with that, we'll continue.